great pleasure to introduce you, Professor Tracy Slatyer. So she completed her undergrad work with honors in theoretical physics at the ANU, Australian National University, in 2005. She is Australian, I just figured out today. So, her doctoral work was in physics in Harvard in 2010 under the supervision of Douglas Finkbeiner, right? Finkbeiner, that's the correct pronunciation. Yeah. Yep. She did a 3-year postdoc at IAS, which I met her at Princeton. Almost we have a similar period of postdoc by the time I was at Canada. So I came to Princeton, I met her. And then she joined MIT physics department in 2013, and she was promoted to associate professor in 2018. And she's received a tenure in 2019. Congratulations, by the way. And she was awarded 2014 Bruno Rossi Prize of American Physics Society, American Astronomical Society, sorry, 2018 Henry Primakov Award for early career particle physics by the Division of Particle and Fields in the American Physics Society, and 2019 Presidential Early Career Award for Scientists and Engineering. And most recently, she was awarded 2021 New Horizon in Physics Prize. So congratulations again, Tracy, for you. And so she is a well-known expert in dark matter. And I believe that today we will learn a lot from her about windows in dark matter. And I remember, I mean, this seminar is what we joint organized with UKZN University of KwaZulu-Natal in South Africa, also with Purple Mountain Observatory in China. And I mean, Purple Mountain has a lot of people involved into the DAMP experiment, the dark matter particle exposure. I believe there will be a lot of interesting conversation, interesting discussion after this. So now the floor is yours, Tracy, please. Thank you.
Well, thank you very much for the invitation and for the very kind introduction, Yinche. I'm very pleased to be able to chat to you all through Zoom. So today I want to tell you about work that I and other people have done over the last few years for a number of searches for dark matter using astrophysical and cosmological data sets. And as Yinche said, I hope to provoke discussion. I know that there are many of you here who have played a role in getting the kinds of data that I'm going to talk about in this talk and in thinking about their applications to dark matter and to other subjects. So I'm looking forward to your thoughts. So I want to begin by just giving a bit of an overview of the puzzle of dark matter and why I spend all my time thinking about it. So what we think we know and what we think we don't know, and why I think that looking at astrophysical and cosmological data holds a lot of promise for testing properties of dark matter that we don't yet understand. And then I want to sort of split the rest of the talk into two components. I first want to talk about the possibility that non-trivial dark matter physics, non-gravitational dark matter physics could have had observable effects on the early universe, which we can measure using sensitive observational probes of the early universe today. So I want to say a little bit about what we can do by testing light dark matter with the cosmic microwave background. This sets very stringent constraints on annihilating and decaying dark matter. And then I want to talk about more recent work on how dark matter can change the temperature history of the universe and how that can be probed at the moment with the Lyman-alpha forest and hopefully in the future with 21 centimeter observations. Then, if time permits, I want to jump forward in time from the epoch of reionization to our galaxy and give you a bit of a status update on this gamma ray excess in the Milky Way that I and others have been thinking about for an order a decade now. I want to tell you a little bit about the analysis methods that we've developed to try to separate dark matter signals from backgrounds and their possible pitfalls. And I want to tell you about the current arguments for and against this excess being dark matter versus a new and unexpected pulsar population versus something else, and how we might disentangle those ideas. So I will fire away. So let's begin with just the overarching question, which I would like to see an answer to before I retire, ideally, which is, what is the dark matter of the universe? So we know some things about dark matter. The title basically refers to two properties, that to a good approximation, the dark matter doesn't seem to scatter, emit, or absorb light. It may have some interactions with light, but they're at a level that we have not yet observed. So really, this is transparent matter, not dark matter. Light just goes straight through it. So that's the dark part of the title. The other part of the title is that this stuff has mass, it gravitates, hence the matter. So probably the most precisely measured parameter that we have, that we know about dark matter, is that it's about 84% of the matter in the universe. This percent level precision measurement comes from looking at the fluctuations of the cosmic microwave background radiation, which I'll say more about in a little bit. But essentially, this gives us a measurement of the fraction of stuff that has the equation of state of matter, but does not interact with electromagnetism, and hence does not feel radiation pressure in the early universe. And that is the stuff that we are labeling as dark matter from a cosmological perspective. So we believe that this component in the early universe that doesn't feel radiation pressure also forms the primordial scaffolding for the galaxies that we observe in the present day. So this plot on the right is a simulation by a number of people, including some of my colleagues at MIT in the Illustris collaboration. From the bottom panels to the top panels, we're moving from early times in the universe's history to later times. The panels on the left are the dark matter structure, and the panels on the right are the visible structure. So the idea here is that over time, dark matter forms this filamentary web of structure in the cosmos. And dark matter is really in the driving seat here, the visible matter, because it's most of the mass in the universe. The visible matter is gravitationally attracted into regions of high dark matter density. And so in regions of the gas infalls into regions of high dark matter density and seeds the galaxies there. So as time moves on, you see this web becoming more and more defined. You see these regions of high dark matter density at the nodes in the web, and you see the gas density following this web, lining up with these nodes and forming the regions of high gas density and high star formation that we call galaxies. So we believe that behind every galaxy, or almost every galaxy that we see in the cosmos, there is an invisible dark matter halo, which is why the galaxy is there in the first place. So it's the backbone, the invisible backbone for the whole visible universe. Now, related to that, and this is an ahistorical presentation, because the way that we actually figured out how dark matter exists in the first place was going from the other direction, was saying, we observe that galaxies appear to be surrounded by halos of this dark matter. So the sort of cartoon picture here is on the right, that when we have spiral galaxies like our Milky Ways, they are surrounded by clouds, it's shown as spherical here, but really sort of more football-shaped triaxial halos of dark matter, which is, so we can predict those halos from simulations of structure like the ones I just showed you, but we can also measure their presence directly from the orbital velocities of stars and gas clouds. And the moment seems to be a very consistent picture that the 84% of matter that we see in CMB can give rise to structure that agrees with what we observe in the present day, modulo some small scale possible discrepancies that are still under discussion. So these are all positive properties, but everything, the modeling to this point really just depends on the fact, on these first two properties, that dark matter interacts gravitationally but doesn't feel radiation pressure. So the last property that we have is an upper bound, that if dark matter interacts with other particles except through gravity, it does so weakly or not at all. And our rationale for that statement is that we've done a lot of searches for non-gravitational interactions of dark matter, and as yet we do not have a firm possible positive detection, although there have been a number of hints of things that might be positive detections, especially in astrophysical and cosmological searches. So that's what we think we know, and that already tells us quite a lot. It tells us that if dark matter is some kind of particle, then it can't be explained by any of the known particles in the standard model. Neutrinos come the closest as things that are neutral and not electromagnetically interacting and don't experience radiation pressure, but neutrinos move too quickly to form the cosmic scaffolding that I showed you and to explain the structure of halos around galaxies and galaxy clusters. So that leaves a lot of open questions, with the big one being, okay, so what is this stuff that we are looking at? But you could subdivide that into many questions. You know, what is this made from? Are we talking about one new particle? Are we talking about many new particles? Are we talking about a whole dark sector? Are we talking about ancient tiny black holes that were formed in the universe's earliest history and still exist in the present day? Where did it come from? How was this stuff formed in the first place? Has it always been there? Was it produced at some point in the universe's history? Was there more of it at some point and it got depleted? Does it actually interact with ordinary particles except through gravity? If so, what are those interactions? And we could keep going like this for a long time. There are a lot of things that we do not understand about dark matter and would like to understand. But the challenge of dark, so you might think at this point, okay, I should come up with hypotheses for what dark matter should be. And the theory community is ahead of you. So this is a plot taken from a talk by my colleague Tim Tate as part of the snowmass process in the US in 2013. We're now going through a current round of that snowmass planning process to try to figure out what particle physics in the US should be doing over the next decade. But this is a 2013 era sketch of some ideas, a non-exclusive list of some ideas for what dark matter could be. I do not want you to, I'm definitely not going to talk about everything on this slide, but I want to take away sort of 3 general points. So everything within this red region is a possible idea for a class of scenarios for what dark matter could be. Everything outside the red region are possible broader topics or questions in particle physics that dark matter could be related to. So point 1 is, we have many ideas for what dark matter could be. That doesn't mean we've hit the right one, but it's not hard to come up with scenarios that would explain the properties that we have currently observed. The second is that dark matter could be a key to much more physics than the baseline question of what is 84% of the matter in the universe doing. Dark matter could be related to new fundamental symmetries of physics. It could be such as supersymmetry, could be the lightest supersymmetric particle. Dark matter could be a hint that there are extra dimensions in our universe that we don't normally see. It could be some Kaluza-Klein tower of dark matter particles that annihilate producing leptons. It could be related to the physics of the Higgs sector. It could be related to deep unsolved problems in the theory of the strong interactions. If it's an axion, some kind, it could be related to the strong CP problem. It could be related to mysteries in the neutrino sector. It could be some kind of new sterile neutrino. It could be the best handle that we have on whole new forces of nature, which are experienced by dark matter, but not by visible matter, in the same way that ordinary matter experiences electromagnetism, but dark matter does not. So the dark matter puzzle is a huge puzzle on its own. It could also be one of our best keys to unlock understanding of other physics beyond the standard model. So the third thing that I want you to take away from this plot is that probably at most one of the options on this plot explains the bulk of the dark matter in the universe. Like, most likely the answer to what is the dark matter in the universe, either all or all but one of the options on this plot are incorrect. But at present, they're all consistent with the data. They all satisfy the properties that I told you on the previous slide. So then the question becomes, okay, so how do we tell which, if any of these, are actually the right answer for our universe? And for that, there's a huge experimental program to try to answer that question, but much of that experimental program focuses on trying to positively detect non-gravitational interactions for dark matter particles. Because if you could do that, you could immediately eliminate the vast majority of possibilities on a plot like this. Okay, so what I've told you so far, I hope, is that we've already learned a lot about dark matter from astrophysical and cosmological observations. We've drawn useful information from many data sets, ranging from studies of galaxies and how stars and gas clouds in galaxies move, to light emitted when the universe was a tiny fraction of its present age, from the cosmic microwave background and from observations of large-scale structure formation. And a lot of that information also comes from data that we already had years or decades ago. So these data are really rich in the present day and getting better all the time. So how can we use them to test different ideas for the nature and origin of dark matter? So one sort of entry into that problem is say, okay, what are some generic ways that dark matter might interact with the standard model or with other dark matter particles? So if we just try to write down some generic interaction structures, one possibility is that dark matter particles could annihilate away. So you could have a situation where 2 or more dark matter particles could collide with each other, then, a miracle occurs. The question mark represents the new physics that we would like to probe, and some visible particles are produced. I've written it like 2 standard model particles here. That is definitely not a requirement. There could be more than 2. These could be quarks, they could be leptons, they could be gauge bosons, they could be any of the particles of the standard model. And if produced, most of the particles in the standard model are unstable. So through processes that we understand, if these particles are produced, they will then typically decay and produce some spectrum of the long-lived known particles. So that's photons, electrons, positrons, protons, antiprotons, maybe some nuclei and antinuclei, and neutrinos and antineutrinos. So this is sort of just a generic process that can happen in many, albeit not all, dark matter scenarios. The question of does it happen at a rate that we can detect is a separate one. Again, it can in some, but not all of the scenarios for dark matter. There is a general class of scenarios where there is some reason to think that the annihilation cross-section has a particular value. In those scenarios, then these interactions between the dark matter and the standard model populated a bath of dark matter particles in the early universe that was in thermal equilibrium with the standard model. That corresponds to a dark matter abundance much higher than in the present day. So in these scenarios, we started out with a lot of dark matter, and then this exact annihilation process depleted it, leaving the 84% of matter in the universe that we observe. So in that case, our percent level measurement of the abundance of dark matter translates into a percent level estimate on this annihilation rate in the early universe. And so that gives us a benchmark to look for in a lot of these searches. Again, it's not a guarantee. There are other ways to produce dark matter and get the right abundance of dark matter that don't run through this annihilation process. But it's a convenient benchmark to look at. When I draw a line that says thermal relic cross-section on subsequent plots, that is the cross-section I mean, the one that the annihilation cross-section that depletes the dark matter to get the right abundance in the present day. And it has a numerical value of about 2 × 10⁻26 centimeters cubed per second, which in particle physics units corresponds to an inverse mass scale of about 100 TeV if your coupling was 1. If your coupling was 10⁻², like in electromagnetism, this corresponds to a roughly TeV mass scale. And that's sometimes called the Wim miracle. But this more general statement that if you have a cross-section around this size, you can get the right relic density for free, that's a more general statement that doesn't really depend on the mass of the dark matter. So we could, if we think about other generic interaction structures, another possibility is maybe you don't need 2 dark matter particles in the initial state. Maybe you can just have 1 dark matter particle that decays into visible particles. And there are variations of this, like maybe the dark matter doesn't have to decay completely. Maybe it decays from 1 dark matter-like state to a lighter dark matter-like state. Maybe in the limit where dark matter particles are primordial black holes, they can decay away slowly via the emission of Hawking radiation. So the picture here is basically you're just converting mass that's stored in the dark matter into visible particles, which again will decay, and we can look for the products of that decay. So again, this doesn't have to happen. It had better not happen with a lifetime shorter than the age of the universe, or the dark matter wouldn't be around today. But you could have a decay with a very long lifetime that would still be consistent with all the observations. So if either of these processes happen, an annihilation-like process or a decay-like process, then it gives you a way to convert energy density that is stored in the mass of the dark matter into visible particles that we can look for. So this leads to a slow trickle of energy from the dark sector into the visible sector over time. And we're going to explore the effects of that energy transfer over the history of the cosmos. Now, we can also rotate these diagrams. Maybe you don't need to look at just things that start with dark matter particles and produce standard model particles. You can look at scattering. You could have dark matter particles bouncing off standard model particles, transferring energy to them that way. You can also, I'm not going to talk about this much today, although I'm happy to discuss it in questions. You could also have a situation where maybe the dark matter doesn't interact with the standard model at all, except gravitationally, but it has interactions with other dark matter particles. In that case, obviously, you won't be looking for the direct products of the scattering, but the energy transfers can still leave observable effects in the observed distribution of dark matter. If dark matter scatters off standard model particles, we can look for the recoils of the standard model particles, and the energy transfer can in this case lead to cooling of the standard model particles if the dark matter sort of is colder and acts like a refrigerant. So these are some sorts of generic interaction structures that we might look for, and we can ask the question of, okay, how would we look for these experimentally? So of course, there's a huge multifaceted search program for these kinds of signatures. I'm not going to be able to talk about them today. There's a standard classification that's based around these generic interaction structures in this sort of two particles go to two particles picture, which is indirect detection. What I've talked about is the annihilation example. Two Chis produce standard model particles. Direct detection, you flip the diagram and have dark matter particles bouncing off standard model particles. You look for the recoils in these tour de force super sensitive underground experiments, or in accelerators, you can collide standard model particles together and try to produce the dark matter particles. And these are sometimes colloquially referred to as you can break the dark matter through annihilation, you could shake it via direct detection, or you can make it at accelerators. So there's a long history of classic searches in these categories looking for dark matter at the GeV and higher scale, with especially those models with abundance set by their annihilation. There's also been a ton of work in recent years to extend these searches to look at lighter dark matter particles below the GeV scale and to consider scenarios where the cosmological history is not set by annihilation. Again, I'm happy to talk more about this later. It's not going to be my focus today. Today, I'm going to focus in on this break it and decays and similar scenarios and what we can do with cosmological and astrophysical data sets. Okay, so starting with the early universe as our test bed. I want to answer the question that I want to ask and give you some ideas on how to answer is, so if we had these processes present, and I'm going to focus on annihilation and decay. So this is an energy transfer from the energy stored in the mass of the dark matter to visible high energy particles. How would that energy transfer reshape the early universe? And how can we see that? And if this is happening, how can we test for it observationally? Okay, so there are people on this call who spend a lot more time thinking about the epoch of reionization than I do, but for those who don't, let me give you just sort of a brief summary of the time period that I mean when I say the early universe. So it's convenient to measure epochs by redshift, so z, so 1 plus z gives the factor by which the universe has expanded since this time. We are currently at z equals 0. I'm going to be looking mostly at the epoch between, z equals 2 and z equals 1,000. So a redshift's higher than z of 1,000. The universe was filled with a tightly coupled plasma of electrons, protons, and photons, plus dark matter and neutrinos, and it was almost completely ionized. So this was when the universe was linearly more than a factor of 1,000 smaller than it is today. Photons at that time could not travel very far because they were rapidly scattering off the ionized plasma. But around redshift 1,000, or a little bit before, the universe had expanded and cooled to the point that the electrons and protons in the ionized plasma wanted to preferentially bind into hydrogen atoms. So at that point, the ionization level dropped off pretty abruptly, and the photons began to stream free from the ionized plasma. Those are the photons of the cosmic microwave background radiation, and we observe them today in telescopes like WMAP and Planck, and a wide range of other instruments. And so this gives us a snapshot of what the universe looked like at redshift 1,000, which corresponds to an age of a few 100,000 years. So this is the oldest light that we measure, and it's the earliest direct observation of our cosmos, although we have some indirect evidence from like nuclear abundances of events that happened earlier. So there are basically two pieces of information that we can pull out of the cosmic microwave background. We can look at its spatial, there are many pieces of information, but they can be classified in two ways. There's the spatial information, which looks at the pattern of oscillations in density and temperature in this plasma across the sky. That shows up as this spatial pattern of hot spots and cold spots in the sky. This is an image from the Planck collaboration. We can also look at the energy dependence of the cosmic microwave background. It is an incredibly perfectly measured black body. This is data from PHIRAS from 1990 or so. But so these points of data, the line is a fit to a black body spectrum. These error bars are 400 sigma error bars. So this is an incredibly precise measurement of the black body spectrum. But we actually haven't measured this black body spectrum since PHIRAS in 1990. There are some proposals for new experiments that could beat down the error bars on this by another several orders of magnitude and start to see interesting things here. So one thing the dark matter annihilation or decay can do is modify either this energy spectrum or this pattern of spatial anisotropies in ways that I will discuss for you in a moment. But moving forward so the CMB is the oldest light I'm going to look at. So what happens after the CMB is emitted? For about the next 100 million years, the universe goes through the period we call the cosmic dark ages. The gas is almost completely neutral. There are no stars. The only illumination of the universe is this cosmic microwave radiation background. And so the universe is steadily expanding and its temperature is steadily dropping. So, however, eventually that cosmic web that I was talking about forms, the galaxies form within the cosmic web, the first stars start to form, and the cosmic dark ages are ended with cosmic dawn, when the first stars turn on and begin to heat and ionize the ambient gas. And this sort of starts around, well, I would say it starts around Z of 20 to 30. It ends when there's sufficient ionization to almost completely ionize the universe, and we return to this ionized plasma state at the epoch of reionization, which happens around Z equals 6. So at the end of this dark ages period and during cosmic dawn, we can hope to measure 21 centimeter radiation from the hyperfine transition of neutral hydrogen, and observing that absorption or emission line can give us a measure of the temperature of the gas during this period and of the amount of ionization. So the sort of toy picture of this is we've got atoms that are illuminated by the cosmic microwave background. They start out with some continuous black body spectrum, which is the CMB spectrum that we looked at before. Depending on how hot the gas is relative to the CMB, you can either get preferential de-excitation of this line, in which case you see emission lines, that's if the gas is hotter than the CMB, or you can have absorption lines if the gas is colder than the CMB. I'm simplifying this, happy to go into more detail for the experts. But there are a number of both current experiments and future planned experiments which are aiming to search for such a 21 centimeter signal. And this would be an entirely new probe on both the distribution of hydrogen gas in the early universe and how hot it is and how ionized it is. This could potentially probe the cosmic dark ages and epoch of reionization. If we move forward even further in time to after the universe is mostly reionized, there are still clouds of neutral hydrogen around. It never ionizes completely 100%. So light passing through those clouds can again give you absorption and emission signals and can produce what we call the Lyman-alpha forest of absorption features in the spectrum. So this video on the right is going to show you as light passes through these hydrogen clouds, you expect to see absorption features showing up. As time goes on, those absorption features get redshifted. This is a nice movie due to Andrew Ponson. And so we see this lion structure. That can also be used as a measurement of the temperature of the universe. The temperature of the hydrogen gas affects how wide these absorption features are, and it affects just how these hydrogen gas clouds are distributed in the first place. So there are several recent studies that have compared measurements of the Lyman-alpha forest with simulations and have gotten an estimate of the gas temperature in this epoch. So observables that we have. So we have the CMB, which tells us what the universe was doing at redshift 1000. We have, so that gives us sensitivity to a lot of things that could have modified the universe between redshift 1000 and the present day. And then we also have these atomic emission and absorption lines from the end of the cosmic dark ages and the cosmic dawn, which unlike the CMB can give us a sensitive measurement of the gas temperature and also potentially a better measurement of the late time ionization history. So what can dark matter, annihilation, or decay do to affect these observables? So this is going to be all back of the envelope estimates, and then I will give you a brief advertisement of how we actually do the calculation. But let's do some back of the envelope estimate first and understand what our sensitivity is going to be. So one possibility, dark matter, annihilation, or decay, if it produces high energy particles, that could ionize the gas during the cosmic dark ages. So during this epoch when the universe is otherwise very neutral, there aren't any stars, there aren't a lot of sources of high energy photons, but dark matter could be a source of non-thermal high energy photons. So let's just work out how much power there is from that process. So let's first just say, okay, suppose we took the mass in hydrogen. What fraction of the mass in hydrogen would we need to liberate to ionize all the hydrogen in the universe? So the mass of hydrogen is about 1 GeV. The ionization energy of hydrogen is 13.6 eV. That's 8 orders of magnitude. So if we were to annihilate 10 to the minus 8 of the baryonic matter, then if we would convert that much of the baryonic matter to energy, that would be sufficient to ionize the entire universe. Now, we would really have noticed if the whole universe had been ionized during the cosmic dark ages. It would have just stopped the CMB photons from propagating. It turns out our measurements of the cosmic microwave background are sufficiently sensitive that we can actually see the effects of about 1 in 1,000 hydrogen atoms getting ionized during the cosmic dark ages. That's how well we can measure the CMB. And there's about 5 times as much mass in dark matter as there is in hydrogen. So what this tells us is that if 1 in a billion dark matter particles converts its mass into energy, into standard model particles, and an order 1 fraction of that energy goes into visible particles, that's enough power to ionize half the hydrogen in the universe. So from what I've told you that the CMB has sensitivity to about 1 part in 10 to the 3 ionization levels, this tells us that we should be able to constrain scenarios where about 1 in a trillion dark matter particles is annihilating per Hubble time during this epoch. So that's, okay, so let's use that as a benchmark. Well, let's use the 1 in a billion number as a benchmark, keeping in mind that this is a huge signal in ionization. So we can ask about changing the energy spectrum of the CMB, that perfect black body spectrum that I told you before. It's been measured to about 1 part in 10 to the 5. So if 1 in a billion dark matter particles were to annihilate, it could ionize half the universe. What would it do to the CMB spectrum? It turns out the answer here is actually not a huge amount, because the energy densities in radiation and matter were equal at redshift 3000. And since then, the relative amount of radiation relative to matter has been going down by a factor that scales just as the redshift. So in the present day, there's about 1/3000th as much radiation energy density as there is matter energy density. So let's take that 1 in 3000 number, say, okay, there's not that much, the amount of radiation energy density in the CMB is about, less than 10 to the minus 3 times the amount of dark matter energy density in the universe. But now if 1 in a billion dark matter particles annihilate, okay, so then that's, so then the amount of energy you're injecting will be less than 1 part in 10 to the 6 of the total energy in the CMB. And what we've measured in the CMB is distortions at the 1 part in 10 to the 5 level. So this is actually a very hard signal to see, just because there's a lot of energy in the CMB. But if we can do future measurements of the CMB that are better by several orders of magnitude, this might start to become competitive, and it can give you a handle on physics going on before the cosmic dark ages. So I'm not going to talk about this much today, but this is a handle for early changes. What about heating of the gas? So I said that if we could heat the gas, it could modify atomic emission absorption lines. So how much could annihilation change the gas temperature? So down to about redshift 200, the CMB and the ordinary matter are expected to be pretty tightly coupled to each other in temperature. So you would need to heat the whole CMB, not just the matter. And then the same estimate applies for spectral distortion, and you don't expect to change the temperature much at all. Like you expect to change it by 1 part in 10 to the 6, which is not going to be observable, no matter how well your no matter how wonderful a 21 centimeter observation you can do. But the baryon number density is 9 orders of magnitude smaller than the photon number density. And so for redshifts less than 200, the baryon temperature is no longer locked to the photon temperature, and any heating of the so at redshifts less than 200, the heating is divided by between a much smaller number of particles. So if I say 1 in a billion fraction of the mass energy in dark matter was liberated, that corresponds to increasing the baryon. So again, the mass in dark matter is about 5 GeV per baryon. So this corresponds to increasing the baryon temperature by about 5 eV per particle. If you heat hydrogen by 5 eV per particle, that corresponds to a 50,000 Kelvin temperature increase. That's quite a lot. Those of you who were observant when I flashed that quick graph of temperature measurements during the reionization epoch, it was mostly around 10,000 Kelvin. Before the reionization epoch, temperatures are much lower. We could expect the gas temperature to be down at the level of 50 Kelvin at redshift 200. So, 500 Kelvin at redshift 200. But I mean, it could be lower than that. It could be down to 50 Kelvin by the time you get to redshift 20. So again, in ionization and in heating, 1 in a billion dark matter particles annihilating is a huge signal. So that's the back of the envelope estimate, and that gives us reason to believe that looking at these signatures could give you sensitive constraints. So just to summarize, ionization is a really powerful probe of annihilation and decay for redshifts less than 1,000. Spectral distortion could be, but mostly what it probes is physics at higher redshifts or non-ionizing processes, because it's hard for it to compete with ionization. Heating isn't really probed by the CMB, but as we start to get measurements of the temperature of the universe at late times, this could potentially be a pretty sensitive probe as well at redshifts less than 200. Okay, so this is just an advertisement. This is the back of the envelope estimate. To study these effects in detail, what we need to know is how the cascade proceeds. If you inject a high energy particle into the universe through annihilation and decay, how does it transfer its energy into heating of the gas, ionization of the gas, low energy photons? So my excellent student and former student, Greg Ridgway and Hongwan Liu, wrote a nice Python package to model these energy loss processes and production of secondary particles, taking into account the cosmic expansion and redshifting, taking into account that the background ionization level could be changing throughout this. And this package is called Dark History, and it's publicly available here, and we welcome beta testers. So you can, having done that work, you can use this to just figure out what are the changes to the ionization history and what are the constraints. So I'm just going to show you that. So dark matter annihilation on the CM, so the effect of dark matter annihilation that changes the ionization history. So changing the ionization history changes the CMB because you produce free electrons that can scatter the CMB photons. That effect on the CMB turns out to be pretty universal for dark matter with masses between about a keV and over a TeV, in the sense that all dark matter models, independent of what particles they're injecting, unless they're neutrinos or otherwise close to invisible, basically affect the spatial distribution of the CMB in the same way. There's a model-dependent normalization factor, but aside from that, it's a characteristic imprint of dark matter annihilation on the CMB. That means that you can do one analysis, you can look for that imprint in the CMB data, and it gives you a constraint on essentially all annihilation channels over a huge mass range. So this is what the constraints look like. This is from the Planck collaborations paper in 2018, based on my results from 2016. So basically, these different colored lines correspond to annihilation into different standard model final states. Everything above this line is excluded, and these lines continue, well, so for annihilation into sufficiently light particles, these lines continue with more or less the same slope down to keV masses. This black line is the thermal relic benchmark cross-section that I told you about earlier. So basically what this tells you is that the thermal relic cross-section for annihilation can be ruled out for any dark matter that annihilates dominantly to stuff in the standard model that is not neutrinos for masses below 10 GeV. So if you want light dark matter below the 10 GeV scale, you need either an origin mechanism that doesn't go through this thermal relic annihilation, or you need to suppress the annihilation during the period of the CMB. It's not crazy to have suppressed annihilation. Like, for example, if you have both dark matter and anti-dark matter, and the anti-dark matter all annihilates away in the early universe, then that will suppress your signal in the CMB. So like, there are definitely models in this space, but this like immediately gives you some pretty general information about what models of light dark matter can and cannot be allowed. We can do the same exercise for decay, for constraints on decaying dark matter from ionization. This is what the bound looks like on the right. So now the y-axis is the lifetime of the dark matter, x-axis is the mass of the dark matter. Everything below this lifetime is ruled out. These colored lines are from an analysis of photon data from our galaxy. And you can see that this one analysis from the CMB does like somewhat better than this whole combination of photon data from a whole range of telescopes. This sets some of the, although there's a caveat here, there's a limit over here for from the Voyager telescope, which has now gotten out beyond the heliopause and can thus measure cosmic rays in the interstellar medium. And that actually sets a pretty tight constraint on the higher end of this mass range. But these CMB bounds set some of the strongest limits on relatively light dark matter, decaying especially to produce electrons and positrons. And because this is a measurement from very early in the universe's history, it also constrains components that are not dark matter, but which were present in the early universe, but then decayed away before they got to the present day. If such a species decayed right around the time of the CMB, we can rule out species that have abundances as low as 10 to the minus 11 of the dark matter abundance today. So that's from the CMB, from the temperature constraints at the moment, just using the Lyman-alpha forest that I told you about earlier. So to do this, we did, my students and former students and I did this in a paper that just came out very recently. So we can compare, so we can take a dark matter model, compute the temperature history with dark history, and compare that to the temperature measurements extracted from the Lyman-alpha forest. There's a bit of a subtlety here because these measurements apply after reionization. So a lot of stars have turned on at this point. So there's a question of what model should we assume for ionization? And we need to account for the interplay between ionization and heating. If the universe is already ionized, then you're not going to get a lot of extra ionization from dark matter, but you will get more heating. So we did a set of different limits here, which are various levels of conservative in assumptions on the baseline ionization history. The most conservative limits is you assume the only source of heating is dark matter, and you just require that that not overheat the universe in the absence of any heating from stars. So that's obviously kind of unrealistic. But for example, this panel is the constraint on decaying dark matter from the lifetime. Everything below these lines is ruled out. Blue is most conservative. Red, the orange band covers some actual realistic models of reionization. And the black lines are the CMB constraints that I just showed you, which, as I said, are like some of the best constraints in this band. And you can see like it's very competitive. And in particular in this low mass band, even this like super conservative approach to the Lyman-alpha limits is setting the strongest constraints that we have. The right panel is the same for annihilation that's velocity suppressed. For annihilation that's not velocity suppressed, the CMB bounds are better. Okay, now that's Lyman-alpha. At the moment, now if we could get a good confirmed measurement of the 21 centimeter radiation, we could do much better, because then we could potentially measure higher redshifts where the baseline temperature of the universe is expected to be much smaller. So if we could say, if we suppose had a 21 centimeter measurement that measured the 21 centimeter brightness temperature to be minus 50 millikelvin at redshift 17, then you can figure out what kind of limits that would give you, and that's shown in this lower left plot. The black line is the current CMB bound on decay. Again, higher lines are stronger. The red line is what you would get with that kind of sample 21 centimeter observation. You could improve the constraints by 2 orders of magnitude. So signals that are currently totally unobservable would show up as strong, like early heating signatures in 21 centimeter. Now, there has been a claim by the EDGES experiment of a primordial 21 centimeter signal already. If you take that, now EDGES actually saw a really, really deep absorption trough corresponding to really, really cold gas, which is hard to explain in standard cosmology. So in that case, you need to put in other new physics to try to explain why the absorption trough is so deep in the first place. But we tested what constraints you could put on extra heating in the presence of other new physics to produce the EDGES trough. And we found that, yeah, in general, the picture is the constraints can get better by 2 orders of magnitude beyond what we currently have if the EDGES result is confirmed. So 21 centimeter results will be a very powerful constraint, especially on decaying dark matter, or have the potential to discover something really new. Okay, so in my remaining 15 minutes, I want to change track a bit. So that was my advertisement for why we should think about how dark matter could affect the early universe. But now in my remaining time, I want to change track a bit and tell you about dark matter searches from our galaxy. So here, the challenge is, again, how would annihilation signals manifest, and how can we tell them apart from other sources of particles and radiation? So we live inside a dark matter halo. So in some sense, it's extremely natural to look for dark matter annihilation and decay products from our galaxy because it's really close. It's all around us. It's the brightest source of annihilation and decay signals we expect to have. Unlike the early universe, we don't need to model some kind of chain of processes where we inject particles and they cool down and they heat or ionize the gas, and then we look for the effects of that heating and ionization. It's a much more direct search. We can just look for the injected particles directly. So I said earlier that the particles you're going to be looking for are photons or neutrinos or charged cosmic rays, and there's an enormous ongoing experimental effort in all these directions. There are searches for charged particles, such as with DAMPI, which is mentioned earlier, and AMSO2 and CALAT. There are searches for neutrinos with experiments like IceCube and Antares and Super Cameo Candy. And there's a wide range of searches for photons, such as with the Fermi Telescope, HESS, Veritas, HAWK, the LASO experiment in China. So this is a huge ongoing effort. It's often challenging to understand the backgrounds in these searches, especially when we either have to model non-trivial propagation effects or we have to look at regions with complicated astrophysics. So let me give you an example of an excess that has gotten a lot of interest as a possible signal of dark matter annihilation, but which I still think we do not know where it's really coming from. So the galactic center excess is an apparent new gamma ray component that was found in public data from the Fermi Gamma Ray Space Telescope by Lisa Goodenough and Dan Hooper back in 2009, so a bit more than a decade ago. So, and I got involved in this in 2013 when, together with Dan Hooper, we found that this excess isn't just at the galactic center, but extends throughout the whole inner galaxy. The Fermi collaboration confirmed it in their analysis of 2016. So spatially, if we look at all the photons around the inner galaxy after we subtract off point sources, they mostly trace the disk of our galaxy. This is expected. Most gamma rays in this energy range come from particles interacting with the come from cosmic rays interacting with the gas in the starlight of our galaxy. We subtract off a model for those backgrounds, and there's a lot under the hood in the subtract off a model of those backgrounds. What we're left with is kind of a roughly spherical blob at the center of the galaxy. So spatially, that is what the excess looks like. Spectrally, if we look at the energy spectrum, so this is not a perfectly measured black body like the CMB, this is a gamma ray spectrum that appears to peak at about 1 to 3 GeV and falls off at higher and lower energies. These red and black points are data points with statistical and systematic errors from an early analysis. The blue point is a dark matter model that has been fitted to it. The kind of dark matter model, if this was coming from dark matter annihilation, the kinds of models that would explain this excess would be tens of GeV to 100 GeV dark matter annihilating through channels that just nanomolar particles that hadronize. And you have quite a lot of choices in that category. So what would we expect from a dark matter signal in our galaxy? So we would expect the signal to follow the dark matter halo, which is roughly spherical in its inner parts. We often model the density of the dark matter halo as a function of distance from the galactic center R with a profile like this one I've written here. This is the Navarro-Frank-White profile. Basically, at small distance from the galactic center, this is just a power law. This is just density scaling like R to the minus gamma, where gamma is the inner slope index. And in the classic Navarro-Frank-White profile, we expect gamma around 1. In contrast, the background looks like this. It mostly comes from cosmic rays interacting with the gas and with the starlight. So as a first approximation, it traces the gas in the galaxy, which is brightest along the galactic plane. We can look at energy and spectral information as well. The backgrounds from cosmic rays interacting with the gas are mostly smooth and power law-like. They can vary over the sky as cosmic rays diffuse and propagate through our galaxy. The dark matter signal that we're looking for would have a characteristic energy scale associated with the mass of the dark matter, so it can have a peak. And we should expect that spectrum, if it's coming directly from dark matter particles annihilating to stuff that decays and makes photons, we should expect that spectrum to look the same everywhere because it's just set by the particle physics. So the galactic center usually has the brightest signal, but the backgrounds are also really hard there. So how do these expectations compare to the galactic center excess? So what provoked a lot of interest in the excess is that these analyses that we and others did around 2014 showed that the spectrum of the excess looks pretty consistent everywhere. This is from an analysis in Caloria, Hollis, and Weniger in 2014, where they subdivided the region around the galactic center into all these subregions, 1 through 10, and then they plotted on the right the spectrum of the excess in these different subregions, and you see there's pretty much always this consistent bump around 1 to 3 GeV. The excess looks approximately symmetric around the galactic center, so that's also good if you think it should be tracing the dark matter halo. It's steeply peaked towards the galactic center. If you interpret it as an annihilation signal, it corresponds to a power law profile with an index of about 1.2. And I said this sort of naive expectation was around 1. Now, later work has showed that you can also pretty well describe the galactic center excess as something that looks like it traces the galactic bulge in stars, plus a central stellar core of stars. My personal view is that at the moment, these systematics in the background are sufficiently serious that I am not sure we can reliably tell the difference between a spherical signal and a signal that looks like the galactic bulge. So, but if we could really confirm for sure that this signal looks like the galactic bulge, it would be a pretty good indicator that this is probably not dark matter, it's probably something to do with stars. So I just want to mention that there have been several studies that I think have made the argument at least that a distribution that traces the galactic bulge plus a central stellar core is as consistent as something that looks like the dark matter halo. But okay, so these properties are why this excess has gotten a lot of interest as a dark matter signal. The other one is that the size of the excess is very consistent with what you would expect from the thermal relic dark matter annihilation cross-section. So if we think about, two hypotheses here, there's the one that makes particle theorists very excited, which is that this is dark matter annihilation. But there's also this possibility that it should be what particle physicists call conventional astrophysics, i.e. anything that doesn't require modifying the standard model. So the scenarios most discussed there are that we're looking at some new population of stars or other point sources, and the most discussed candidate in that category is that we're looking at millisecond pulsars. So these are spinning neutron stars. The other possibility is that there's some kind of new diffuse background in this area, say from some kind of outflow or burst from the galactic center. But the reason why the pulsar hypothesis has gotten so much attention is that, so on this right panel, I'm showing the spectrum with statistical errors only for the excess. There are large systematic errors at low energies. The black line is a dark matter fit, so it works quite nicely. It has the thermorelic cross-section, that looks good. But these dashed lines show the observed spectra of detected pulsars and populations of pulsars in Fermi. And you can see that at least above about 1 GeV, the spectra look really similar to what we observe. And at low energies, the systematic errors are large. So that's like a strong argument that what we could be looking at here is not dark matter, but instead a new pulsar population. So over the last few years, there have been these pulsar wars about, is what we're looking at a population of pulsars or something else, which could be an exotic dark matter signal. And back in 2016, my colleagues and I, as well as another group in Amsterdam, decided to try to distinguish these hypotheses by basically looking at how grainy the signal was. So the idea was that a dark matter signal should be pretty smooth, should look the same towards all directions as we look at the galactic center, whereas a point source signal would have a bunch of hot spots and cold spots. Now, obviously, if the point sources were bright enough, the hotspots would be very pronounced and we could just identify them directly from the data. So the point source hypothesis here is that there's a population of point sources here that are just below, that are somewhat below the level of individual detectability, but we still might be able to see the granularity of the population. You can think of this as, we might be able to see like a whole bunch of 2 sigma sources, even if none of them rise to the level of being 5 sigma. So there were 2 analyses in 2016 that both claimed evidence for point sources. There was my group's result where we looked at the non-Poissonian statistics of fluctuations from an unknown point source distribution. And there was the Amsterdam group, which used a wavelet-based method to try to look for small scale power above expectations from the diffuse backgrounds. So the wavelet-based method recently got reanalyzed by a group by Yiming Zhang and collaborators from Fermilab. And so what they found, so they ran this wavelet analysis, and as previously as in 2016, they found a bunch of high significance peaks in this area. So there are point sources in this area, which is what the 2016 group found. And they said, aha, that's evidence that we're seeing a population of point sources. But what Zhang et al. Did was they compared this list of peaks to sources that have now been identified in Fermi. And they found that this wavelet method is now at this point mostly finding sources that have already been identified. So like, that's good. The wavelet method found these sources in 2016. Fermi didn't put out this catalog until like last year. So wavelet method was ahead of its time. But now we know what most of these sources are. And we know that most of them are not actually near the galactic center. They're just along our line of sight and cannot be part of a galactic center pulsar population. So it turns out that when you mask all of these known sources, it doesn't really reduce the galactic center excess at all. So they're in the same region as the galactic center excess, but not necessarily contributing to it. So this upper panel on the right, the blue line is showing what the excess looks like before you mask these sources. The orange line shows what the spectrum of the excess looks like after you mask these sources. You can see there's not very much difference. You can take the sources that could potentially still be part of a galactic center excess pulsar population and add up their total emission. And from that, you get this green line. So this is about 10% of the 10 or 20% of the total flux. So what that tells me is that there could still be point sources contributing to the galactic center excess, but most of them need to be pretty faint, like not something that we can currently detect with the wavelet approach. So the wavelet approach is not currently like finding sources that clearly contribute to the excess. But that's fine. There could still be fainter sources there. So because I'm short on time, I'm just going to sort of skip over the details of the Poissonian template fitting method and give you the result. But the idea here is to use the fact that if I've got a population of point sources, then the number of photon observations are not uncorrelated from each other. If I see photons from one pixel, it tells me there's a source in that pixel and increases my probability of seeing more photons from that pixel. For that reason, the statistics are non-Poissonian. I can model the sky as a linear combination of different physical contributions. So emission from particles cosmic rays interacting with the gas and starlight, and possible emission from a dark matter signal, other contributions like these giant gamma ray structures called the Fermi bubbles, And in addition, I can model a linear combination of unresolved point source populations, which trace and these could be extragalactic sources, which are approximately isotropic, or sources tracing the disk of the galaxy, or point sources in a galactic center excess pulsar population. And I'm basically just going to model the sky as a linear combination of all these components and then fit and try to understand what the data prefers in terms of weights for these different components. And the thing that distinguishes population of point sources explaining the excess to dark matter explaining the excess is just that their statistical properties are different. And that in the point source case, we have a higher chance of getting hot spots and cold spots. So when we did this analysis in 2016, what we found was that there was a pretty strong preference. It looked like there was a pretty strong preference for the excess to be entirely point sources. This plot is showing the posterior probability distribution to have a certain fraction of flux for the excess in point sources versus smooth emission. This inset is where we don't allow there to be point sources associated with the galactic center excess, and the red line is the posterior for the dark matter component, and it's peaked around 7 or 8% of the total emission in this region, being this smooth dark matter-like contribution, which is what we would expect from previous studies of the excess. But then in the main plot, we allowed for a galactic center excess point source population. Its posterior is the yellow line. And you see that in this case, 7 or 8% of the emission gets allocated to point sources in this new population, and basically 0% gets allocated to the smooth emission. So in 2016, we said, okay, we're done. What we're looking at appears to be a new population of point sources, most likely pulsars. So, however, in the last couple of years, together with Rebecca Lean, who's an excellent postdoc now at Stanford, we found some reason to reconsider those results. Again, I'm pretty much at the end of my time, so I'm just going to tell you the basics. So this is the one-slide summary of everything that's happened on this in the last couple of years. So in 2016, we found that the field had a pretty strong preference to assign all the galactic center excess flux to a new point source population. And that was with significance around 6 sigma. I mean, really, it was a Bayesian analysis. The base factor was about 10 to the 9. But in 2019, Rebecca and I reran this analysis and went, there's actually something fishy about this analysis, because it's not actually preferring to assign 0 flux to the dark matter component. If you let it run into the non-physical region of letting the smooth contribution go negative, it wants the smooth contribution to be really negative. So that is an indication that something is wrong in the analysis. A consequence of that is that if you inject a dark matter signal on top of the real data, the fit can't get it back until you make the signal like 5 or 6 times larger than the excess itself. So this is a problem. The root of this problem, we said at the time, was almost certainly that our model for the backgrounds is not good enough. Like, our model for the backgrounds is leading to the fit trying to assign part of the photons to a point source population that is bigger than can physically be there, and pushing the smooth contribution down to compensate. So then there were 2 papers by a group on which I'm not a co-author, Chang et al. And Bushman et al. Last year and earlier this year, that said, okay, let's try using better background models. Let's give our background models more flexibility, more freedom. Let's see what we can do. And so they showed that you can quantitatively explain this, the smooth component wanting to go negative, which is very unphysical, by the original background model we used being bad. And they said you can construct newer models which don't prefer this negative coefficient. So that's nice. Using these better models, you can rerun the analysis from 2016. And now it's not a 6 sigma preference for point sources anymore. Now it's more like a 3 sigma preference for point sources. So the preference goes down by a lot, but there still seems to be some indication for a point source population. But then Rebecca and I came back to this problem and said, okay, but are we really sure of this? And we showed that there can be another systematic problem, which is that if your model for the signal isn't quite right, then the fit can pick up spurious evidence for point sources as a consequence. So the general idea here is just, suppose that the fit prefers a somewhat different morphology for the signal than was specified by the signal template. So suppose you want to look like the bulge instead of something spherical, or suppose that your signal is actually a little bit different in the northern sky and the southern sky. which could be real or could be an artifact of a background mismodeling, because the background's very different in the north and in the south. So then you can ask the question of, okay, is this easier to explain with point sources or smooth emission? And the answer will always be point sources, because point sources give rise to a signal with higher pixel to pixel variance. And that is the exact signal that the non-Poissonian template fitting method is latching onto to try to tell what is point sources and smooth emission. That in point sources, you are allowed to have pixels that are more different from each other, because you say one pixel has a point source in it, the other one doesn't. So there's a toy example here, but but this is the basic idea. If I were to say that, you know, my model wants more photons in the north than in the south, it will always be easier to explain that to saying, okay, I have a bunch of point sources and more point sources in the north than in the south, than by having that be a statistical fluctuation on the smooth contribution, because for point sources, you get to look at this, the error is the square root in the number of sources, and for the smooth emission, it's the square root in the number of photons. So point sources have bigger error bars can absorb mismodeling better. Thus, any kind of mismodeling of the signal can get interpreted as evidence for point sources. So that's the general idea. And we then asked, is that happening in real data? And we showed that, like, yes, it is. So we focused on a 10-degree radius region surrounding the galactic center. And what we showed is that in this region, the data actually prefers the galactic center excess to be pretty asymmetric, like it's brighter in the north than in the south. So when we do our standard analysis on this, and we assume symmetric signal templates, we find that there's a really strong preference for point sources. But then it turns out that if you just say, okay, well, but what if I allowed my signal templates to be asymmetric, to have different brightness in the north and in the south, then the Bayes factor in favor of point sources drops from 10 to the 15 to 7. So Bayes factor is like an odds ratio between models. So in the first case, you're saying, okay, the model with point sources, it's 10 to the 15 times as likely as the model without them. In the second case, you're saying it's 7 times as likely as without them. So this drops from, to less than a 1 sigma preference, basically. So the apparent preference for point sources in this specific analysis turns out to really just be the excess would like to have a north-south asymmetry. It has nothing to do with small-scale granularity. It's just about, it's easier to explain a north-south asymmetry with point sources. And so we can check that in simulations. We can simulate a case where you've got an excess which is 100% smooth, no point sources in it, fit it, but it's asymmetric between the north and the south. And then try fitting it with just a symmetric smooth component plus a symmetric point source component. And you see that the results look exactly like what we see in the real data, both at the level of how much power gets allocated into the different templates, and at the level of, you can look at the inferred source count function for the point sources, which is the function of how many point sources you have as a function of their brightness. This upper panel on the top right is showing that result for the real data. The blue line is the galactic center excess population of point sources. And the lower line is showing what happens in this simulation, which has 0 galactic center excess point sources in it. So this kind of error predicts an inferred point source population very much like what we see in the real data. So then that suggests that maybe the apparent point sources in the real data might not be really there. Okay, so where does that leave us? So at the moment in the gamma rays, so there are ways that we can make progress in the gamma rays. We can try to do more flexible background and signal modeling to try to avoid these systematic errors. We can try to use entirely different other methods. There's some work being done on machine learning to try to distinguish these signals. But one way to shortcut these gamma ray systematic uncertainties entirely would be to say, well, if it's pulsars, we can look at different frequencies. If it's pulsars, they should be emitting in the X-ray and radio as well. And there was a very nice paper by Francesca Colore and collaborators in 2016 that said that once MeerKAT has the opportunity to look at the region around the inner galaxy, MeerKAT could potentially see tens of pulsars from this population. And if you could see 30 pulsars that are distributed like the galactic center excess, then I think we would be done. I think we would know what the answer is at that point. And SKA, once fully operational, could see hundreds. So this might be episode 3 of the Pulsar Wars, might be if MeerKAT comes out in a few years and says, yep, we found the pulsars, then I think we would feel that we have understood the excess. Okay, so sorry for being a bit over time, but yeah, I'll just wrap up there. Dark matter is about 80% of the matter in the universe, and we don't know what it is, although we have a fair bit of information about it. I hope I've convinced you that these astrophysical and cosmological data sets are extremely rich and can potentially provide pretty stringent tests of the non-gravitational properties of dark matter over a wide range of possible scenarios. We need to both understand how to predict the kinds of signals we could get and how to disentangle them from ordinary astrophysics. Constraints on extra ionization and heating during the dark ages and the cosmic dawn already are placing pretty robust and powerful constraints on dark matter annihilation and decay. 21 centimeter observations, if we can make them, will potentially improve the limits on decaying dark matter in particular by a pretty large factor. We've done dark matter searches in the inner Milky Way. There is this excess there, which is not yet fully explained. It may be a new and hitherto undiscovered population of pulsars, but the systematics that we've identified in some of these analyses suggest that the apparent preference for pulsars could just be spurious. So probes in other wavelengths would be one way to potentially resolve that and tell us what's really going on with the galactic center excess. And I will stop there. Thank you very much.
Well, thank you, Tracy. Thank you for this very nice talk, comprehensive indeed. Okay, so now we open the floor to questions. Aru, what's the size of dark matter? What's the size of dark matter surrounding galaxies, or bracket, what radius?
Yeah, so the dark matter halo in the Milky Way extends quite a long way out on the stars. So I mean, of course, like the dark matter density never drops to zero. It just merges into the cosmological density at some point. But we usually talk about the virial radius within which the density of the dark matter is like 200 times the critical density of the universe. And for the Milky Way, I think that's about 200 kiloparsecs. So for comparison, we're about 8.5 kiloparsecs from the center of the galaxy. So the halo extends out a long way. That said, we do, as I mentioned this Navarro-Frank-White profile, in simulations, we do expect the dark matter density to rise pretty steeply towards the center of the galaxy. So like the dark matter density at our location around the Earth is expected to be about 5 to 6 orders of magnitude higher than about 6 orders of magnitude higher than the cosmological dark matter density. And as you go in closer to the center of the galaxy itself, you expect the scaling to be roughly 1/r for the density in an NFW profile so at some point that 1/r scaling is going to cut off. It could, like even in dark matter only simulations, it will turn over at some point, but there's also, there is this unknown issue that the simulations that really get a 1/r scaling all the way in are often simulations that only have dark matter in them and don't have visible matter. Once you turn on the effects of visible matter, you can produce like flat density cores. So the 1/r scaling can stop, order like a kiloparsec from the center of the galaxy. So it still goes up from where we are, but then would be expected to flatten out at some point. But I think my understanding is that like for dwarf galaxies, the expectation for cores is pretty strong, but for Milky Way scale galaxies, I don't think there's a lot of evidence for big flat density cores in simulations. But if there were cores significantly smaller than the kiloparsec scale, then it would be hard to tell from some of these simulations. Now, if the galactic center excess was really dark matter annihilation, then we would have measured the dark matter profile much better than we've ever measured it before and into much smaller distances than we've ever measured it before. So like a confirmed signal and indirect detection would tell you a lot about the properties of the dark matter halo, but it's hard to observationally constrain the profile at the very center of the galaxy without a signal like that, because the baryons dominate the dark matter in that region anyway. So in terms of just looking at the gravitational potential, you're mostly looking at what the ordinary matter is doing, not what the dark matter is doing.
Dr. Yu Gao, near the end of the slides, when you mentioned observing the pulsars in microwave, does that mean spatially resolving them as point sources?
I think yes. It means measuring the pulsations. Like there are definitely going to be a whole bunch of radio point sources in this region. The way that this has worked, so there have already been some searches for this, like with the Green Bank telescope, for example. The way that the strategy with Fermi has often worked is that if you see a pulsar, and again, the people in the room who know more than me about this should definitely feel free to speak up, because pulsar searches are not my primary area of expertise. But the way that it's often worked with Fermi is, so you see something that you think might be a pulsar based on its spectrum in the gamma rays, but it's often hard to see the pulsations in the gamma rays because photons are rare, like gamma ray photons are rare. So, but you can say, all right, there's something that I think might be a pulsar. Let me follow it up first with a radio telescope to just try to measure its spectrum in the radio. And if the spectrum looks promising from the perspective of it being a pulsar, then let me do a pulsation. Then let me like spend more time staring at it with Green Bank and try to do a pulsation search. And that approach, I think, has been fairly successful in confirming a number of suspected gamma ray pulsars at other frequencies. But yeah, so when I say detect as pulsars, like the real smoking gun for it to be a pulsar would be to see the pulsations. But an intermediate step might be to see that you observe a radio source with the kind of spectrum that looks like a pulsar. But yeah, but like just finding points. Yeah, I learned this a few years ago when I was like, oh, let's try to cross-correlate Fermi data with like known point sources in this region. It was like, every Fermi pixel has many, many, many radio point sources in it. Like a thing to keep in mind here is that Fermi's angular resolution is not good by the standards of radio and X-ray experiments. It varies from about 0.1 degree at high energies to worse than 1 degree at low energies. And the kinds of sources that we're talking about here are not producing a ton of photons in the Fermi data set. Like you're maybe talking about 10 or 20 gamma ray photons over the 10-year lifetime of Fermi. So that means that the localization isn't great. So like in GBT, what you need to do is, if you want to try to confirm one of these sources in Fermi, is like find the Fermi hotspot, but then scan back and forth over it, because the Fermi localization like radius is bigger than the GBT field of view. So you have to do this mosaic. I think Meerkat will be in better shape in this regard, but like it's still true that Fermi can that Fermi's angular resolution is much worse than its counterparts in the radio, and so there'll be a lot of sources within Fermi's localization radius, but probably not a lot of pulsars. Like we haven't really detected pulsars, especially millisecond pulsars in the galactic bulge. Yeah.
I would like to ask about the dark history. Have you tried interfacing? Have you tried interfacing it into the camp, or perhaps the 21 centimeter fast?
Yeah, we
just hold on. I also have that question. So let me add my question to the answer. So it's interesting to know this dark history code because CAMP just outputting the CMB and 21 cm fast basically operating that evolution from dark ages to the EOR. So what is the redshift range that this dark history would work, and how you basically connect or bridge with the existing code with CMB and 21 centimeter? Thank you.
Yeah, good. Yes, so there is an interface to class with an earlier version of the calculations that go into dark history. The history leading up to dark history is that back in 2015, I made a big set of tables which said if I inject a particle at some energy and some redshift, assuming some baseline ionization history, how do those particles transfer their energy into heating, ionization, and low energy photons as a function of redshift? So class has this module, I think it's called exoclass, that reads in those tables basically. Like I didn't do this, I think this was like Vivian Poulan and colleagues wrote this module, which basically reads in those tables and works out the changes to the, and feeds that into the evolution equation for the ionization history. And like CosmoRec has a modification that does this as well. And it's, I mean, all our early CMB constraints were done by using this kind of stuff with class. This works really well for the CMB. Like, just if you're only looking at the CMB constraints, you don't need the full machinery of dark history, because the flaw in this is that you have to assume a base. You have to assume that the redshift tells you everything about the ionization level and the gas density. And if you want to change like what ionization history you're considering, you have to go back and rerun everything, which is not very feasible. So this doesn't really matter for the CMB constraints, because they're coming, like the CMB constraints on Annihilation, that are mostly controlled by redshifts of around 600 for Annihilation and around 100 or 200 for Decay. So the background ionization level is very small. Then the modifications that you can do with dark matter Annihilation are also pretty small, because if they're large, they get ruled out. So it's not a bad assumption in those circumstances to say, okay, we're just going to assume it's the background ionization level. Like, this is way before ionization. You don't have to worry about when stars turn on. But if you want to, yeah, I like these transfer functions. I think I started them from redshift 4000, and they run nominally down like to redshift 3 or something, but they're not very good once you hit the epoch of reionization, because I think the original version doesn't include reionization at all. So like, it still has the ionization level of the universe of being 10⁻⁴ at redshift 3 or whatever. I made other versions of them which had like a step function reionization at redshift 6. But in reality, this is not what you want to do, right? I mean, like you want to be able to scan over the uncertainties in your astrophysical reionization at the same time as you vary the exotic physics. So that latter thing is what dark history does, because dark history, rather than making these big transfer tables, what it uses is basically the transfer function at each time step. It says, if I inject a high energy particle into the universe at some redshift with some ionization level, then what happens in the next DT? Like, what secondary particles are produced in the next like small interval of time? And then, so you can take whatever ionization history you want and include back reaction and basically just string together a whole bunch of these transfer functions. And that gives you the flexibility to handle arbitrary ionization histories. So in terms of, interfacing, but for the CMB, this is overkill, because the CMB constraints.
May I just shortly interrupt? Just one additional question. So yes, I totally understand this dark matter and basically effect in this code. But what about the reionization part? Did you and Liu, Hongwan Liu and Greg to use some successful code to produce the standard reionization part and modify that to plug the dark matter in, so that you will get a complete DM version of the reionization?
That is something that I want to do, and we have been talking to the authors of some of these codes to handle it. At the moment, the way that it works is basically that so at the moment, it's not fully interfaced. At the moment, the way that it works is you take your models, like you take a model for how much photoionization and how much photoheating do I have from stars, and you plug that into dark history as a source of ionization and heating, and then you solve and then you solve self-consistently with both the astrophysical sources of photoionization and heating, and photoionization and photoheating, and the sources from dark matter. And that like takes into account how the cascade evolves in circumstance of changing ionization history. That's what we used for the Lyman-alpha constraints. We basically just tried varying the parameters of these photoionization and photoheating models that have been considered in the literature. This is, I think now, but of course, if you want to look at like so we would like to interface with 21 centimeter fast. There's also like another thing that we're actively working on here, which is at the moment, dark history still treats the gas as if it's homogeneous, which is, so it can be effectively true for some regions of parameter space, because some of these particles that are produced in annihilation can have extremely long path lengths. So then when you look at the energy deposition, you're basically just averaging over extremely large volumes. And so then it's not a bad approximation to say that the gas density is approximately homogeneous. But you can also have circumstances where most of your power is going into particles that have a rather short path length. And so the heating and ionization happens mostly at the source of the annihilation. And so like then it matters that your annihilation is pretty inhomogeneous because a lot of it is happening in dark matter halos, and that your cooling may also be inhomogeneous because some of it depends on scattering off the gas. And so, you know, if you inject in a region of high gas density, then you'll cool a lot faster and deposit a lot more energy. So this is what we are actively working on right now, is how to incorporate the inhomogeneity properly and how to be able to incorporate it into codes that calculate the 21 centimeter signal.
Okay.
So yeah, like at the moment, what this is for is, you tell it your overall amount of photoionization and heating, and it will tell you how the overall temperature of the universe should evolve, including the effects from exotic heating, and it will tell you like the spectrum of particles that you get from this cooling cascade. But there's definitely more to be done in this regard, and in particular for the 21 centimeter power spectrum, there's more that like needs to be done. We're not ready to do those constraints yet. So the estimated constraints that I showed you on decay are actually just from a global 21 centimeter signal. They don't use any information from the power spectrum.
Yeah. But power spectrum certainly provide a lot of information. Since you are in MIT, so HERA is one of the major focus, and here as well. I mean, myself and my student Montosisi here also involved into that HERA. So sooner or later we'll get some upper limit on the power spectrum, and possibly in the future some cross correlation results. So having a solid package that can make prediction would be very valuable in that sense.
Well, I'm glad you feel that way. I also feel that way. We're working on it. I will hope to maybe I can come back and give you an update in a year or two on having a good package for this.